All right. Okay. So I think we should start.
So
good afternoon, everyone. Welcome to Warwick Stochastic Finance Seminar. Today is our great pleasure to have Professor Saeed Hamadene from University of Le Mans to give a talk on mean field reflected backward SDE. So let me first say something about Professor Hamadene. So he is a world well-known expert on BSD and especially reflected BSDs. So if you have any questions or if you have any problems, want to discuss with Professor Hamadene about the BSD, you're welcome to stay after his talk. Now I give time to Professor Hamadene, and he will talk about mean field reflected BSD. Thank you, please.
Thank you, Liang. Thanks a lot for the introduction. Thanks a lot also for inviting me to give a talk in this seminar. So as you can see, the title of the talk is mean field reflected backward stochastic differential equations, which is joint work with Boualem Djehiche and Romuald Elie, Djehiche in KTH in Stockholm, Sweden, and Romuald Elie in Université of Marne La Vallée in France. So, yeah, what I want to mean by mean field reflected BSDE? It's an equation of this type. Okay. Yeah, here we have a backward equation, which means that we fix the terminal value psi. It is reflected, as you can see, because the solution, which is y and z and k, and which I will precise later on, the solution should be greater than an obstacle, and we should also have this condition satisfied. Why? Because basically in this equation, the process k, which is increasing, will make that this condition yt is greater than h of yt, expectation of yt satisfied, and this process, this increasing process, I mean, in a way, it is weight, which makes that this condition is satisfied. And I mean, we are not allowed to add any weight, but we are allowed to add only a minimal weight in such a way that this condition is satisfied, which means that we require this condition, which is called Skorod condition, and satisfied, which means that the process K acts only when y reaches the obstacle. Here, the process Z is some kind of control. The role of Z is to make that the processes Y and K, they are adapted. I mean, it is of mean field type. Why? Because basically, as you can see here, the function f depends on the expectation of y, and the obstacle h depends also on the expectation of yt. Okay, this is why we call those equations of mean field type. What are data of the problem? As you can guess, the data of the problem, they are basically they are Brownian motion here. The terminal value psi, which is f capital T measurable, where the ft is the completed filtration generated by the Brownian motion B, psi the terminal value, f the driver of the BSD, and h the implicit obstacle are given. Those are the data of the problem. As I mentioned it previously, a solution is a triple yzk of adapted stochastic processes. Okay, they should be adapted. Okay, adapted. Y is and k, they should be continuous, and K should be increasing. This is what we mean by solution of this mean field reflected BSD. Xi, as I told it is the terminal value, or I mean the terminal wealth or target wealth, which is reached by Y. H should be understood as solvency threshold, which I will give an example which motivates this reflected BSDE. I mean, in few minutes, and H should be seen as the solvency threshold, and F should be seen also as the infinitesimal utility. Okay, those are the meanings of all those items. So, as I told you, YT is the current value of Xi. Z is control process. I mean, it's a process with which we act in such a way that the things they should stay adapted, and at capital T, YT is equal to Xi, and K should be understood as consumption process which can be withdrawn from the wealth without making that YT at capital T is equal to Xi. I mean, K is consumption process which you can withdraw from the wealth YT, and at the same time YT is equal to Xi. This is why we require that K should be specific. I mean, K should not be an increasing process, an arbitrary increasing process. This is consumption. This is the allowed consumption process. Okay. Now, what's the motivation of the study of those BSDs? We consider a portfolio, large number N of homogeneous life insurance policies. Okay, the indexation of the policies is L. YLN, ZLN, they are characteristics of the prospective reserve of each policy. YLN says the value of the life insurance, and ZLN is in a way how to invest in financial market in such a way that the life insurance policy will reach its objective. And we consider the case of nonlinear reserving, which means that the infinitesimal utility of the life insurance L is given by function f. Okay, it's given by function f, which depends on the value of the life insurance L, and also it depends on the other life insurances. And this nonlinear reserving is equal to alpha t, which is some kind of fixed utility, minus delta t y L capital N T. This term is some kind of actualization. Is the actualization. Delta t is the actualization coefficient, and the utility has also another term which is equal to beta t, the maximum between some kind of fixed value theta t, and the maximum between theta t and YL minus this this average value of the other life insurances. Okay, now this is for what concerns the utility of the life insurance. Now, there is a threshold for this life insurance, which is equal to H, and the threshold is given by this quantity. This is a threshold, fixed threshold U. Those are, I mean, minus C. This is some kind of fixed management fees, and also a term which is related to the behaviors of the, I mean, of the mean value of the life insurances with respect to this fixed threshold. I mean, this is the threshold. I mean the life insurance YLN should be kept in such that it should be greater than this threshold. This function H is a threshold. Now, if we send capital N to infinity, what we get? We get, I mean, function which depends on YT, and also which depends on the expectation of YT. If the life insurances, they are independent, I mean, this term can be approximated, but its expectation and the other terms can be also this term can be approximated by the expectation. The same for that one. What we get, I mean, we get some kind of model point, okay, a model point where for the life insurances, where the utility of the model point life insurance is given by F, which depends on the value of the life insurance, and it depends also on its expectation, which is equal to that one, which this function is obtained when we take capital N going to infinity in the previous quantity. The same for the threshold. For the same threshold, we have threshold like that. As you can see, it depends also on the expectation of YT. Okay, and I mean, pricing this type of contracts is the main motivation of considering the BSDE, which I introduced previously. Okay, this is the main motivation. I mean, the main motivation of those BSDs, they come from insurance. Okay, so now since the subject is related to reflected BSDs, even if they are of mean field type, I'm going to introduce at least briefly the meaning of standard reflected BSD, because I mean there are there is, I mean, an obvious link. What does mean standard reflected BSD, which is associated to function F and terminal value Xi and barrier S, or sorry, here the barrier is L. Okay, the barrier is L, sorry, with the barrier L here. Okay, barrier L is a triple of adapted stochastic process YTZ KT. As previously, the K is an increasing process, which makes that this condition is satisfied, and it acts with minimal energy, which means that K acts only when Y reaches the obstacle L. As you can see here, there is now mean field term. There is nothing which is related to expectation of YT or the law of YT. This is standard reflected for BSDE. Those BSDs, they have been introduced by El-Karoui Allais in 1907 in order to assess the American options, and also they are related to PDEs with obstacles, or you can find them also in mixed stochastic control. So now those BSDs, those reflected BSDs, they are connected with the notion of a Snell envelope of processes. So I'm going to recall what does mean Snell envelope process. We give ourselves, I mean, stochastic process U, which we suppose that, I mean, which is right continuous with left limits, CAD-lag in French. Okay, it is CAD-lag stochastic process U. What does mean Snell envelope of U? It's just the smallest CAD-lag super martingale such that ZT is greater than UT. It's a small super martingale which dominates U. It has the following representation. It can be represented as essential supremum for stopping times tau which are greater than T of the expectation of U tau known FT. This is the representation of the Snell envelope of U at T. Okay, so if I'm going to show some pictures in order to show how things work for the Snell envelope of stochastic processes. So if, for example, U is here in, if U is here, okay. Yeah, I mean, the Snell envelope of U, as I told you, is just the smallest super martingale which dominates U. If things they are deterministic, super martingale is just decreasing function, as you can see here. Snell envelope of U is that one. Okay, this is smallest decreasing function which majorizes U, as you can see here. This stopping time, the first time where U and Snell envelope of U reach together is optimal. Sorry. Yeah, if as I told you, the U is right continuous with left limits, is RCLL, okay? RCLL now, previously in the first case, U is continuous, okay? U is continuous. U is continuous. Here, U is continuous. Now, if U has some discontinuities, what are the consequences for the Snell envelope of U? As you can see, when U has negative jumps, okay, when U has negative jumps, in this case, Snell envelope could have jump, okay, could have jumps. And the jump of the Snell envelope of U occur only when U has negative jumps. And here, okay, here, it is U, the jump of U, okay, this is the jump of U. This is the jump of the Snell envelope of U. As you can see, the Snell envelope, when it restarts from this point, okay? It starts from this point, okay, from this point. This is the Snell envelope of U. Wait a minute. Okay, now if U has a positive jump, as you like here, okay, like here, Snell envelope of U does not have jumps. It is continuous, and Snell envelope of U is the figure in red. Okay, this is Snell. This is, as you can see, when U has positive jumps, Snell envelope of U is continuous, and the solution of the reflected standard BSDE has an interpretation in terms of Snell envelope of processes in that way. Okay, in that way, the process, the solution, when it exists, mainly it exists when F is Lipschitz with respect to YZ. Okay, and L is continuous process, and at capital T Xi is greater than L, the process Y has this representation in terms of Snell envelope. It's not necessarily a Snell envelope because, as you can see here, we take the expectation from T up to tau. Okay, if you want to get Snell envelope, you should say plus YT plus the integral of SYS ZSDS, and you add the same quantity here, and so which means that you are going to start from zero. YT plus this term is Snell envelope of this process. This is the link between the Snell envelope of processes and the solution of reflected BSDs. There is, I mean, link. There is link between our reflected mean field reflected BSDs and actually Snell envelope of processes. Okay, so what does mean field, standard mean field BSD? Standard mean field BSD, it's a BSDE, but there is no reflection like that one. Okay, like that one. Yt is equal to xi plus, as you can see here, driver or the generator of the BSDE depends on the law of Ys Zs. So if, for example, this law is of type the expectation of Yt and the expectation of Zt, we get this BSDE. What is the main motivation of considering those BSDEs? Basically, Yt in this case can be considered as say the utility of an average agent in the market, and say in the market or in the economy. Okay, this is the average, the utility of an average agent in the economy. So those are the BSDs of those types. They are of mean field type, and they are standard. And I mean, they have been introduced at the beginning of 2000, yeah, say it, surrounding of 2007 or 2006. And mainly if xi, I mean, if xi is square integrable, f is Lipschitz. With respect to Yz here, it is Lipschitz with respect to those laws. The solution exists and is unique. Okay, sorry, they are considered including Boualem Lee and Peng in 2009, Boualem Djehiche Lee and Peng in 2000. Yeah, it's a limiting model for several agents. As I told you, it could be the utility of an agent in economy. Now I'm coming to reflected BSDs. So there is the first attempt, I mean, in another framework. The framework is not necessarily related to insurance. It is related to risk sharing in financial market. So Boualem, Elie, and Huyen, they have considered, I mean, this kind of reflected BSDs. As you can see, it is backward equation because we fix here terminal value. We have driver here, does not depend on the law of Y. This is an increasing process. What's the particularity of this equation? Here, the reflection is made in terms of expectation. Okay, we have the expectation of LTY. It is greater than 0, and the role of K is actually to make that this condition is satisfied, and it acts in with minimal energy, which means that this corrode condition is satisfied. So what's the main motivation of? So basically what they show if is Lipschitz, we have xi is square integrable, and this consistency condition is satisfied. Mainly L should be continuous increasing, should be by Lipschitz. Okay, by Lipschitz. Then there exists a unique solution of this equation when we require that K is deterministic. Without K deterministic, the solution is not necessarily unique. But at the same time, things requiring that K is deterministic is more or less obvious. Why? Because basically here the constraint is deterministic, since it is constraint in expectation. Now, why considering those reflected BSDs? As I told you, mainly it is related to risk sharing in financial market. If, for example, if you are an agent in a financial market and you sell, I mean, you sell an American option with payoff L, you are going to construct a portfolio in such a way that its value at each time YT should be greater than LT. In this case, I mean, there is no default. Each time that the holder of the American option wants to exercise, I mean, the value of your portfolio is greater than the value of the amount that you should pay for the holder of the option, then we require that YT is greater than LT. But requiring that YT is greater than LT in a way could make that the value of the premium is rather high. So there is another notion which is introduced, say, it seems to me that it's surrounding of 1995, where instead of requiring the YT greater than LT, we require that YT is greater than LT, but only with certain probability, okay? With certain probability. For example, the probability here will be equal to 0.95, okay, or 97, or if I say things like this, so sorry. We require that only the probability of YT greater than LT, which is equal to 0.95, okay. Yeah, which means that, I mean, the seller of the option accept that in 5% of cases, I mean, he can have a portfolio with a value which is strictly smaller than LT. I mean, there is some kind of risk sharing. Now, why this constraint can be related to the previous reflected BSDE, mean-field reflected BSDE. If we take LT of Y is equal to indicator of Y greater than LT minus WT, with W which is equal to 1.95, we take the expectation. You take the expectation. What you get that the probability of YT greater than LT is greater than the WT, which is exactly the subject of I mean of the our discussion, okay, the subject of our purpose. So mainly those mainly those reflected BSDs, they are introduced in order to assess, okay, in order to assess, yeah, to assess, I mean, those American options, but there is some kind of risk sharing between the holder and the buyer, or the holder and the seller of the option. So there are also, I should say that there are also some other papers on mean-field reflected BSDs, but mainly they are related to the linear case. So it's paper by Lee in 2014. What does mean? What does mean? What is our framework? What is our framework? Our framework is YT. As I told you, our framework is that one. Okay, our framework is that one. Is that one? So if a solution of this equation exists, as I told you previously, there is a link between reflected BSDEs and the Snell envelope of processes. So if a solution for this equation exists, then Y will have representation through the Snell envelope of processes, and this representation is the following one. Is the following one. We have YT in this case is equal to, it has the representation through the Snell envelope of processes, and it is here, as you can see here, we have Y, and we have Y, the expectation of Y, we have here Y and the expectation of Y, and so on. Tau, as I told you, it's stopping time, which is greater than this. So which means that if this reflected BSDE has a solution, Y is fixed point of an appropriate application. So we are going, in order to show that the solution of the mean field reflected BSDE, of our mean field reflected BSDE has a solution, we are going to introduce the mapping and to show that it has, I mean, fixed point, which, and then, I mean, the link between Snell envelope of processes and reflected BSDs will provide solution for our BSDE. It will be, actually, we will do it in several steps. Obviously, the function, the mapping is that one. Okay, the mapping is that one. We with phi of Y will be equal to, when we fix process Y, we introduce phi of YT, which is equal to, which is here. Now, in order to have fixed point, we need to show that phi is contraction, and we need also to have Banach space. Which kind of Banach space we are going to consider? It is that one. Yeah, we are going to consider Banach space of continuous stochastic processes Y, such that this they are uniformly P integrable. Okay, which we call SP. SP is the space of continuous adapted stochastic processes, such that this quantity is finite, which is actually Banach space. We consider a case of P is greater than 1. The case of P is equal to 1. I mean, I will say some words how we are going to deal with it, and I will say why P is equal to 1. It cannot be handled in the same way as P is strictly greater than 1. Okay, this is phi. Okay, this is phi. So the first step is to show that when Y belongs to SP, phi Y will belong also to SP. For that, we should suppose that the function f has some kind of integrability, and f and h, they are Lipschitz, and psi is p integrable, and this consistency condition satisfied. Then, if Y belongs to SP, phi Y, defined here, okay, phi Y defined here, belongs also to SP. But this is not necessarily major problem. Why? Because basically what to do is just to work in such a way that the stopping times, they are replaced by something which is independent of the stopping time tau, and this is rather obvious. What just linearize, make some kind of linearization of the function f. What does mean linearizing a function is just if you have a Lipschitz function, you can write it phi y, which is equal to f0 plus some function which depends on y of y, and this is the increment of f between y and 0, and this term is bounded by the Lipschitz constant, the constant of f with respect to y. This is what we do here. This we linearize the function of f of y and the expectation of yt and the expectation of yt. Then we make some kind of majorations. The integral will be taken from not only from t up to tau, but from 0 up to capital T, and we have majoration here. Sorry, we have majoration here. Yeah, actually, everything. I mean, everything. We have here also the conditional expectation. We have here conditional expectation, which means that then what to do, just take here to power p, take the supremum, the expectation. We have here a conditional expectation, which means that we have martingale, and then use Dubs inequality, which is valid, which is that one when P is strictly greater than 1. As you can see, for P is equal to 1, we cannot use this kind of Toops inequality. This is why we have previously required that P should be greater than, should be strictly greater than 1. Yeah, doing like this, we get that for any y in SP phi y will belong to SP. This is the first step. Now, what we are going to do is we are going to show that, I mean, we can solve, we can find fixed point for the function phi, but only in small interval, okay, only in small interval t minus delta t. This is what we are going. We are going to that phi has fixed point, but only when we restrict time to t minus delta and t. Sorry, okay. So there is also another, I mean, condition on the function h. There's also a condition on the function h. This condition on the function h is related to its, as I told you, h of yt, the expectation of yt, which means that we have some kind of y prime. We have supposed that h, this h is Lipschitz. The Lipschitz constant of h with respect to y will be denoted by gamma 1. The Lipschitz constant of h with respect to the expectation will denote it gamma 2. Okay, we'll denote it gamma 2. And we are going to show that there is a solution if gamma 1 and gamma 2, they are small enough. Gamma 1 and gamma 2, they cannot be arbitrary. For example, I mean, if h could be only Lipschitz, requiring that yt is greater than 2yt, okay, 2yt could be not possible, okay, if yt, especially when yt is positive, okay. So which means that there are obvious conditions on the Lipschitz constants of h with respect to yt and the expectation of yt, and this condition is that one, okay. This condition is that one. The gamma 1 plus gamma 2, here is gamma 1, here is gamma 2. We should have gamma 1 plus gamma 2. This condition satisfied. Should be this quantity should be strictly smaller than 1. If this condition, if mainly this condition is satisfied, we can find delta strictly greater than 0, which depends only on p, on the Lipschitz constant of f, gamma 1 and gamma 2, not on t, not on xi, okay, such that the function phi is a contraction on the time interval t minus delta t. Okay, this is what I'm going to show now, and then we will see how to go further in the solution of the mean field reflected BSDE, which I introduced previously. Okay, so basically, it's not very difficult. We take two stochastic processes y and y prime, which belong to SP. We take here the difference. It's a difference of essential supremums. The difference of the essential supremums is smaller than the essential supremum of the difference. As you can see, the terms which are related to xi, they will disappear. Okay. Those terms, they will disappear. We get that, and then we linearize the function f and the function h, and we get now we fix say, and we get what we get. We get, I mean, yeah, we linearize and then we fix delta for now. I mean, there is no condition on delta. Just delta is fixed. We take t, which belongs to t minus delta and t, and then we take this difference here. Therefore, we linearize the function h here. Okay, the function h here. As you can see, the constant gamma 1 will appear, and the constant gamma 2 also will appear. And we do the same for this difference. Okay, we'll do the same for this difference. What we get at the end of the day, that phi y of t minus phi y prime of t is smaller than this quantity. What, as you can see, this quantity is deterministic, which comes from the expectation of y minus the expectation of y prime. Okay, but this term is, I mean, is conditional, is a conditional expectation. What to do next? What to do next? You take, I mean, you take the power p, which means that here we are going to take the power p here. Okay, we are going to take the power p here, and we use this convexity inequality. Since p is strictly greater than 1, what we get at the end of the day, we get that phi y t minus phi y prime t to power p using this inequality. What we get this inequality, okay, which stems exactly from that one. Now we take the supremum, then the expectation. This is deterministic term. Okay, this is deterministic term. But here it's a conditional expectation. Okay, so conditional expectation. Then we are going to use Dubs inequality. Once more, we are going to use Dubs inequality. At the end of the day, what we get this quantity. Okay, we get this quantity. What does mean? What's the link between this quantity and the inequality, which I introduced previously between gamma 1 and gamma 2? If you take delta is equal to 0, you get exactly this term. Yeah, if you take delta is equal to 0, you get exactly this term. Since the limit is strictly smaller than 1, it means that we can find delta small enough in such way. Sorry, we can find delta small enough in such way that this term is strictly smaller than 1, which means that phi will be contraction when we restrict time to t minus delta, and this delta will depend only on CF, on gamma 1 and gamma 2, and also to the power p, which means that we can find the delta such that phi will be contraction on SP t minus delta t, and then it has fixed point. Phi has fixed point. There is a link between Snell envelope of processes and reflected BSDEs. Then the fixed point y on t minus delta t will have a representation as a solution of a reflected BSDE in the following way. We can find K, an increasing stochastic process Z, such that for any t which belongs to t minus delta t, yt is this y and k and z will satisfy this reflected BSD. As you can see, it's mean field reflected BSDE. It's of the type of the ones which we previously introduced, but it's only on the time interval T minus delta capital T. So just to remark, Z and K, they verify the spaces where they live are those ones. Okay, they belong, has this integrability, and K has this integrability, which means that we have, right now we have solved the mean field reflected BSD, which introduced in T minus delta and T. Now since T, which is delta, does not depend neither on T nor on the terminal value, we can solve the same. I mean, we can solve the same reflected BSDE, but in the time interval T minus 2 delta, T minus delta, where the terminal condition is not Xi, but the terminal condition will be Y of T minus delta, where Y2 minus delta is the process which we previously constructed, that this process, okay, which exists. So once more, there is a solution for this reflected mean field reflected BSDE between T minus 2 delta and T minus delta, and then making concatenation, okay, concatenation, which means that we are going to introduce stochastic process Y tilde, Z tilde, and dk tilde, which is, I mean, passing Y and Y bar, Z and Z bar, and K bar, we get solution for the mean field reflected BSDE between T minus 2 delta and T. But we can do the same for T minus 3 delta and T minus delta and so on. At the end of the day, we will have a solution for the mean field reflected BSDE. Okay, then this mean field reflected BSDE has a solution, and the solution is also unique. Why it is unique? Because basically, if there is another solution, okay, if there is another solution, yeah, Bayes-Leroy representation of this solution, phi, the function phi, I mean, the other solution will be a fixed point of phi between T minus delta and T, okay, which means that those two solutions, they will coincide on T minus delta T. Then they will coincide on T minus 2 delta, T minus delta, and so on, which means that the other solution and Y, they will coincide on 0 capital T. So since Y and Y prime they coincide on 0 capital T, we have also the coincidence of the Z's and also the coincidence of the K's, which means that the solution is unique. So then we have shown like this that this mean field reflected BSDE has a unique solution. So are there questions?
Yes. Are there any questions? Is it the end of talk, Said?
Or I can continue. I can resume. I can resume.
Yeah, we can resume, and we will leave the questions in the end.
Okay, if you want.
Thank you. Thanks.
So what about this? What can be said about this? The inequality under which solution existence is unique. As you can see, since P over P minus 1 is strictly greater than 1, this inequality means that gamma 1 plus gamma 2 should be strictly smaller than 1. Okay. Yeah, we should have this inequality implies that one. So this inequality can be also read like this. Just take to the power P minus 1, okay, to the power P, or say just take to the power P. Yes, just take to the power P, and then that this quantity put this term here in order to get this inequality. This one and that one, they are the same inequalities. Now, if we have a look to this quantity, what can be said? Yeah, when you take the limit, when p goes to infinite, this quantity will go to e. Okay, will go to e, while gamma plus gamma 1 is strictly smaller than 1, which means that this term will go to infinite, which means that, I mean, when psi and f, they have the appropriate integrability conditions, I mean, if, for example, they are bounded, we can solve the mean field reflected BSD, because we can find P, an appropriate P, which is strictly greater than 1, such that this condition is satisfied. Okay. Now, when P goes to 1, this quantity goes to infinite, and then this condition will be satisfied when the function h, okay, when the function h with respect to y, this is the y bar, for example, which is related to expectation of y, when the function h with respect to y, I mean, moves very slowly, which means that gamma 1 is very small, or even, I mean, h does not depend on y. Okay, in order to be able to solve the equation, we should have gamma 1 very small. This is the main I mean, conclusions which can be withdrawn from this inequality. Sorry. If gamma 1 is equal to gamma 1 plus gamma 2 is equal to 1, which means that if we consider the limit case, the solution might not exist. Actually, if we take h of y bar is equal to y bar, then gamma 1 is equal to 0, gamma 2 is equal to 1, requiring that yt is greater than expectation of yt cannot happen, at least if yt is a stochastic process. It happens only when yt is deterministic. But in this case, I mean, if everything is stochastic, yeah, finding yt deterministic is rather impossible. So, which means that when gamma 1 plus gamma 2 is equal to 1, there is an important chance that the solution does not exist. Now, I have considered the case, I mean, we have dealt with the case where here f, okay, where here f is, here we have the expectation of yt, here we have the expectation of yt. If instead the expectation, we have the law of ys, here we have the law of ys. So, is it possible to say something about those mean field reflected equations? The answer is affirmative, and the result is that we can replace the expectation by the law of yt. Here the same things, they will work if we require that f is Lipschitz, okay, is Lipschitz with respect to this argument, and what does mean dp? Dp is just the p Wasserstein distance between two measures which belong to which have moments of order p. Okay, yeah. If f is Lipschitz with respect to mu to this component, with respect to dp, which is the p Wasserstein distance, I mean, we can say also that the solution exists and is unique, but I mean, with gamma 1, gamma 2, and p, they should satisfy the previous condition. condition which I introduced in point 9. Okay, yeah, but this is DP. This is DP in terms of I mean, for random variables. Okay, random variables. Now, mainly in order to show that the reflected BSD has a solution, there are two methods. The first one is related to fixed point, as we did in our framework, and there is also the penalization method. So the penalization method has an interest because, for example, if you want to make some numerics, if the penalization scheme converges to the solution, say in simulating the penalization scheme, you will be able to simulate the solution of the mean field reflected BSD. So the question is, do we have a penalization scheme which converges to the solution of the mean field reflected BSD? The answer to this question is affirmative, and we have actually we have results in this sense. If, for example, we suppose that f is increasing with respect to y and y prime, h is increasing with respect to y and y prime, I'm going to take the case of p is equal to 2, okay, because it's easier. It is easy to deal with the case p is equal to 2, but p strictly greater than 1 can also be considered. So in this case, with those conditions, the penalization scheme will converge to the unique solution of the mean field reflected BSD, which means that which kind of penalization scheme? First, which kind of penalization scheme we consider? We consider the following scheme. Sorry. So we first introduce here. Mean field BSD, which are the ones studied by Bogdan, Lee, and Peng. This is mean field BSD, and here those are BSDs. These are standard BSDs, because for n greater than 1, here, as you can see, it depends on the expectation of y n minus 1, which is already evaluated, which we have already calculated. Kn is the sorry, Kn is just this process. As you can once more, Kn is the h of y n minus 1, expectation of y n minus 1, which is already calculated, which means that this BSDE is of standard type. Now, if gamma 1 and gamma 2 term is the following one, if gamma 1 and gamma 2 satisfy the condition 9, which I mentioned previously, with p is equal to 2, then y n, z, and k, and they will converge in S2 times H2D times H2 to the unique solution YZ of the BSD mean field reflected BSD. They will converge to this equation. Mainly the scheme for the proof of this result is rather standard. First of all, we should show that we have an increasing scheme. Which is actually the case, because we have supposed that this is why to have supposed that f is increasing with respect to y and y prime, and h is increasing with respect to y and y prime. Mainly the important point that I should point out is that this is the solution of the mean field reflected BSDE, which is constructed with the fixed point argument. This is the solution. Okay, this is the solution, and showing that yn is smaller than yn plus 1 is smaller than y is rather I mean not very difficult. But without assuming, but if we do not have this stochastic process y in hand, showing that the scheme is increasing is rather easy. But giving bound for those for this sequence is rather tough. I mean, if we do not use this inequality, it's rather tough to show that here we have a bound. Yeah, okay. The bound here is the solution. Now, once we have that, I mean, later on the proof is rather standard. First of all, we can define the limit. The limit, yeah, will satisfy the obstacle condition, and it is also in appropriate space. In first step, we can show that it is right continuous with left limits, but this is not very difficult, since if you have an increasing sequence of supermartingales, the limit is also of limit of increasing RCLL supermartingales. The limit is also RCLL, which means that y hat is RCLL. Next, I mean, because we show that y hat is continuous. Y hat is continuous. Why it is continuous? Because basically gamma 1 plus gamma 2 is smaller than 1. Okay, because basically gamma 1 through the condition 9, gamma 1 plus gamma 2 is smaller than 1, and we have also then y hat will satisfy this this relation expressed in terms of Snell envelope of processes. Now jumps. Then in first step we show that this term here, this term does not have jumps. Then we show that y hat do not have jumps. First, I mean, now deterministic jumps, then now stochastic jumps, then which means that y hat is continuous. If y hat is continuous, it has this characterization. Then the link between Snell envelope of processes and the standard reflected BSDs makes that there exist k hat and z hat, such that y hat and k hat and z hat is a solution of the mean field reflected BSD. But we know that the solution is unique, which means that y hat, k hat, and z hat, they will coincide with y, z, and k. This is the use of the Snell envelope of the penalization method. Okay, we have here now what can be said. As you can see, because I'm seeing that the time goes rather quickly. What can be said if, for example, as you can see, we have dealt with the case where we have only ft of yt, the expectation of yt. If f contains z, we can make that f contains z, but in this case we should majorize, f by some kind function of psi of t, y, the expectation y prime, and for that we should show that there is a solution of the mean field reflected BSD, which is associated to psi h and also psi. Okay, yeah, which means that this we should have specific f depending on z in order to show that the penalization scheme will converge when f depends on z, because basically in the penalization scheme we have shown that yn smaller than yn plus, we should have this y psi, where y psi is here. We can deal with the case with the case P is equal to 1, but in this case, the Y will not belong to S1 because, as I mentioned it previously, for P is equal to 1, I mean, we have some kind of specific Dupes inequality. But if P is equal to 1, the solution should be looked for in the class D of processes, and Z is in appropriate space. H can depend on T and omega. It should be continuous with respect to T. Finally, we can consider the case of two obstacles. We can consider the case of two obstacles, two equations. Okay, as you can see here, we have two obstacles. Y is between H and the G. Once more, F depends on the expectation of Y. Here, since we have two obstacles, we have, I mean, a difference of continuous increasing processes, which make that this condition is satisfied. And as you can see, we have two score-out conditions. Yeah, and there is solution which is unique for this equation when, I mean, the homologous of the condition 9 on the coefficients of H with respect to Y and Y prime, and the one also of G with respect to Y and Y prime. I mean, those coefficients satisfy those conditions. I mean, we should adapt the condition 9 to H and also to G. In this case, we can show that the solution exists and is unique. It seems to me now I have finished. Yeah, I have finished. Thanks a lot for that.
Thank you very much, Said. I think it's a very interesting talk.
Thank you.